Hey guys, Alexander here, and in this video we will be deriving the coefficients of the regression model for a simple linear regression model. So let's get started with some of the important results that we need to be able to derive beta 0 hat and beta 1 hat. So firstly, let's remind ourselves y bar, the mean of y, the sample mean or the mean of y. It's defined as 1 over n times the summation from I is 1 to n of yi. This also means that ny bar is equal to the summation from I is 1 to n of yi. By similar reasoning, we know that x bar is equal to 1 over n times the summation from I is 1 to n of xi. So that means that nx bar is equal to the summation from I is 1 to n of xi. Okay, now there are some important results that we need to know using the summation operator. One of the first of them is that the summation from I is 1 to n of xi minus x bar times yi minus y bar can also be written as any of these following three forms. The first one is the summation of xi yi minus nx bar y bar. Okay, that's number one. Number two is that this summation can also be written as the summation of xi minus x bar times yi. It can also be written in form number three, which is the summation of yi minus y bar times xi. And all of these things are inside the summation operator for number 2 and 3. So let's go about actually showing how this equation, let's just name it A, how A can become 1, 2, or 3. So firstly, let's take A and let's go write it over here in the corner. So we have the summation of xi minus x bar times yi minus y bar from I equals 1 to n. And if we expand the brackets, it becomes the summation from I is 1 to n of xi yi minus y bar xi minus x bar yi plus x bar y bar. And all of these are still inside the summation operator. Now, because of the linearity of the summation operator, we can split these four up into the sum of four summation operators. So it's the summation from I is 1 to n of xi yi negative y bar times the summation from I is 1 to n of xi negative x bar times the summation of yi. And I'll just leave out the from I is 1 to n just for this example because it will speed up the process. But do remember to include it in your writings, or at least say that you've left it out, just so that your professor or your teacher is clear that I have left them out to simplify my derivation process. Plus, this is the summation of n of these terms. So we know that that's just going to be nx bar y bar. So from this result, from this step over here, let me just highlight that. From this step, we can easily go find the results for 1, 2, 3, and 4. For 1, so let's look at case 1, which is over here. It's that this can be written as the summation of xi yi minus nx bar y bar. If we look at these summation over here, these two terms, and we look at the top over here, the first things we did, I told you that y bar is equal to 1 over n times the summation from I is 1 to n of yi. Okay? So that means that ny bar is equal to the summation of yi from I is 1 to n. So this over here can be, this one over here is negative x bar times ny bar. The term over here, negative y bar times the summation from I is 1 to n of xi, well, that's just nx bar multiplied by negative y bar. It becomes negative y bar times nx bar. And then if we bring this term down, we have plus nx bar y bar. And on the left over here, we can see we have from I is 1 to n xi, yi. And what do we see? This, and this all have the same terms in there. So we have two negatives, one positive, that leaves us with one negative. So we can see that that summation can also be written as summation from I is 1 to n of xi, yi, negative n x bar, y bar, because we've got minus 1 here, minus 2, and plus 1, so minus 2 plus 1, minus 1. That's case 1. So we have shown that this summation, the summation of xi minus x bar times yi minus y bar, can also be written in this form. So let's go and show form 2 and form 3, for example. Okay. Just grab a blue pen. So this equation that I've highlighted, this expansion, is the one that is helpful to us to be able to write either form 1, 2, or 3. This is the crucial one we need to use. So to obtain the result for form 2, we want to get xi and x bar as two common factors of yi in the summation operator. So how we end up achieving that is we take the summation of xi, yi, negative y bar times the summation of xi, negative x bar times the summation of yi plus nx bar y bar. And we want to have some terms cancelling out over here. So we want to end up with the summation of xi minus x bar times yi. So we want an x bar and we want an xi. Clearly over here we've got the xi times yi bar. Now so over here we need the negative x bar, which is this part over here. So let's go just simplify these two, bring them down. This is negative, this is negative y bar times nx bar. And this part over here is also nx bar, y bar. So these two cancel each other out. Then that leaves us with the summation of xi, yi, negative x bar times the summation of yi. I'll use the black pen. So we have the summation of xi, yi, negative x bar, yi. Because this summation operator over here, we have a constant outside, which is the negative x bar. We can bring it inside of the summation operator, then we have the summation of negative x bar, yi. This will yield the same result as over here. So then we can write everything under one summation operator. And then we notice if we do some simple factoring, we factor out the yi, we get the summation of xi minus x bar times yi. As simple as that. So we've shown that the summation of xi minus x bar times yi minus y bar is also equal to the summation of xi minus x bar times yi. And this shows us case 2. This is case 2 that's been covered. So lastly, let's take a look at case number 3. So for case number 3, instead of cancelling out the second one, we will cancel out the third and the fourth terms in this highlighted equation. So let me show it to you over here. Let me just pick a better color for it. The summation of xi, yi, negative y bar times the summation of xi. And then we already know that this can simplify to negative nx bar, nx bar, y bar. And we already have this term as positive plus nx bar, y bar. These terms cancel out. So we're left with the summation of xi, yi, negative the summation of y bar xi, which can be written as a single summation operator of the summation of xi, yi, negative y bar xi. Factor out the xi's, so we get the summation of xi times yi minus y bar And thus we have shown case 3. So case number 3 has been shown here. So the summation of xi minus x bar times yi minus y bar can be written in many different forms. Each form can be useful for a different situation that you might encounter. Now, I've done all of these things over here to allow us to easily derive these coefficients for our regression model, the estimated ones, beta 0 hat and beta 1 hat. So these are the coefficients for the simple linear regression model. So let's start with our linear regression model. We have y, in general, we just have, for a simple linear regression, we have yi is equal to beta 0 plus beta 1 xi. And you can see the similarity between this and just a straight line, which it in essence is. It's just y equals mx plus c, where c is now beta 0, m is beta 1, and x is now just xi, and y is replaced with yi. That's the similarity to that. So we just have a straight line that we're going to use to fit by the method of least squares to fit it between data points that we have. So we want to take a bunch of points and we want to fit a line that passes through them such that we minimize this square deviations between the points and that line. So we want to minimize the sum of squared errors. That's what we are trying to do in our model. So this is a population regression model. Your sample regression model or your estimate model is yi hat is beta 0 hat plus beta 1 hat xi. And the sum of squared errors is equal to the summation from I is 1 to n of yi minus yi hat squared. So we want to minimize the distance between our observation. This is the real observation, and this is value of y predicted by our model, predicted or shown by our regression model. So we want to minimize this, and this is a quadratic equation. Okay, so we want to minimize this. So let's go and plug it into, expand this thing, and then take the derivative. So we know this result, and we're interested in deriving beta 0 hat and beta 1 hat because we want to go derive the estimators for our model. We want to derive beta 0 hat and beta 1 hat. So let's go plug them into the SSE equation. So it's a summation from I is 1 to n of yi minus beta 0 hat plus beta 1 hat xi squared. Don't forget the squared. We want to minimize the sum of squared errors. So when we minimize something, we are looking to where its derivative can possibly be set equal to 0. We're looking for a minimum point, not a maximum. We want a minimum point. So we want to look for some point where the curve, this quadratic curve, will look like that. We want a minimum value, not a maximum. We want a minimum. Okay, so we will go and say this is SSE is equal to this. Then let's go just simplify it. It's the summation from I is 1 to n of yi minus beta 0 hat minus beta 1 hat xi squared. So let's go take the partial derivatives of partial SSE by partial beta 0 hat to start off with. And notice that the only term that we have with beta 0 hat in it is inside the expansion in the middle over here, the negative beta 0 hat. So let's take the derivative. It's going to be 2 times the summation from I is equal to 1 to n of yi minus beta 0 hat minus beta 1 hat xi. And we're going to have to multiply by a negative 1 because of the chain rule of differentiation. There's a negative 1 multiplied by the beta 0 over here. So we end up with negative 2 times the summation from I is equal to 1 to n of yi minus beta 0 hat minus beta 1 hat xi. Now, if we're looking for maxima or minima, we need to set our derivative equal to 0. So we equate this derivative equal to 0. So we say 0 is equal to negative 2 times the summation from I is equal to 1 to n, and this part over here. And as we can see, there's a 0 on that side. So let's divide by negative 2 and divide by negative 2 to get rid of the negative 2 on the right-hand side. So we're left with 0 is equal to the summation of yi, is 1 to n, negative n beta 0 hat, because we have got negative beta 0 hat summed n times, so that's n of them, so that becomes negative n beta 0 hat. And this beta 1 hat is also a constant with respect to I. So we can bring that outside of the summation. It becomes negative beta 1 hat times the summation of xi. And remember the results that we derived at the very beginning of this video. This is n y bar, negative n beta 0 hat, negative n beta 1 hat x bar. And this is all equal to 0. See, we can factor out an n out of all of these terms. So we factor it out and we divide by n on the left-hand side. So we're left with 0 is equal to y bar, negative beta 0 hat, negative beta 1 hat x bar. So that means that beta 0 hat is equal to y bar, negative beta 1 hat x bar. And that's that. That's how we derive beta 0 hat for the simple linear regression model. Okay, so let's go over to deriving beta 1 hat. Beta 1 hat, we're going to take partial SSE, partial derivative of the sum of squared errors with respect to beta 1 hat, which is equal to, again, we're deriving this function over here, this one. So it's, and with respect to beta 1 hat. So first step, 2 times the summation from I is equal to 1 to n of yi minus beta 0 hat minus beta 1 hat xi. And now we need to remember the chain rule of differentiation. We still have to take the derivative with respect to beta 1 hat. So the derivative of negative beta 1 hat xi with respect to beta 1 hat is going to be equal to negative xi. And we can simplify this expression to be negative 2 times the summation from I is 1 to n of xi times yi minus beta 0 hat minus beta 1 hat xi. Great. Now, let's equate our first derivative to 0 to find out if, the minimum point. So we equate this to 0 and we solve for it. So we get 0 is equal to the summation of xi yi negative beta 0 hat times the summation of xi negative beta 1 hat times the summation of xi squared. So let's go about looking at what can we do over here. Well, we might think that we are in a bit of a pickle, but we're not. We've derived some results that will make life easier for us. So firstly, let's rewrite this. Summation of xi yi negative beta 0 hat times summation of xi, which is n x bar, negative beta 1 hat times the summation of xi squared. But wait a minute, we've already derived beta 0 hat. So let's just go plug that in. And we have the result from over here. Beta 0 hat is y bar minus beta 1 hat times x bar. So plug that in over here. So we have negative y bar minus beta 1 hat x bar times, back to the blue, n x bar negative beta 1 hat times the summation of xi squared. And over here we have the summation of xi yi. And all of this should equate to 0. So 0 is going to be equal to the summation of xi yi, let's expand these brackets. So it becomes negative nx bar y bar, because we're multiplying out the y bar with negative 1 and nx bar. And the next one is negative times negative, which is positive beta 1 hat nx bar squared, negative beta 1 hat as the summation of xi squared. So we can see over here, we have a familiar friend over here, and we have something that involves beta 1 hat in this term and a beta 1 hat in this term. So let's factor the beta 1s. We get beta 1 hat times nx bar squared minus the summation of xi squared. And on the left-hand side of these two, we get the summation of xi yi minus nx bar y bar. Well, doesn't that look familiar? And yes, it does. It's what we derived in this first result over here. So we can say by deriving case 1, we know that this summation of xi yi minus nx bar y bar, this is in fact equation A, which is the summation of xi minus x bar multiplied by yi minus y bar. So let's go substitute that in and this term over here. So this is the summation of xi minus x bar times yi minus y bar. And this term on the right hand side. So let's bring the beta 1 hat to the other side of the equation. So it becomes beta 1 hat multiplied by the summation of xi squared negative nx bar squared, which is equal to the summation of xi minus x bar times yi minus y bar. And this means that beta 1 hat is equal to the summation of xi minus x bar times yi minus y bar, all of this divided by the summation of xi squared minus nx bar squared. Well, typically the form that you will see it in is having this rewritten in a different form. Well, let's go rewrite this denominator because it's not quite in the form that they want us yet. So the summation of xi squared minus nx bar squared, this is the same as the summation of xi minus x bar squared. And well, how do we go about showing that? Well, I'll just do a simple expansion for you over here. It's the summation of xi squared negative 2 times x bar xi plus x bar squared. And all of this is still in the summation operator. If you simplify it, it becomes the summation of xi squared negative 2x bar nx bar, because this is the summation of xi. It's negative 2x bar times the summation of xi, which is negative 2x bar times nx bar, plus we have nx bar squared that we are summing because it's the summation from I is 1 to n. So plus nx bar squared. So this simplifies to the summation of xi squared minus nx bar squared. So this is equal to the summation of xi minus x bar times yi minus y bar divided by the summation of xi minus x bar squared. And that gives us the formula for beta 1 hat for the simple linear regression model. And there's also another notation that you need to know. This is sxy over sxx, the sum of squared, sum of xy, the sum of xi minus x bar times yi minus y bar, and sxx is defined as the summation of xi minus x bar squared. So this is the whole process for deriving the results for beta 0 hat and beta 1 hat for the simple linear regression model. It's quite lengthy, as you see, but once you have derived these results and you know of the similarities between equation A and the form 1, 2, and 3, then you can very easily and very readily replicate your derivation of this result. Because in many courses you will be asked to derive this and you won't really ever see it being derived for you because the professor tells you to go do it at home. Well, this is how you actually go about deriving beta 0 hat and beta 1 hat, which are the coefficients for your regressors in the simple linear regression model. Thank you very much for watching this video. I hope it's been beneficial and helpful to your education. Boer Commander out.